welcome back to the lesson on limits at infinity. And as promised, we're going to take a look now at limits at infinity in rational functions. And as our first example, I brought in the function f of x equals 1 over x. Pretty basic, pretty simple. And that is because I just want to explain the concept of how it works. And we're going to take a look at more interesting examples as we make progress here. So the limit as x approaches infinity of function 1 over x by direct substitution would be 1 over infinity. If we divide a positive number by infinity, we know that we get almost 0, and because they're both positive, that's a 0 plus. Similarly, the limit as x approaches negative infinity for 1 over x will be 1 over negative infinity. So these two have opposite signs, which means that the answer would be 0 and 0 negative. Now, if you look at the graph, or if we think about the graph of the rational function 1 of y equals 1 over x, and here I'm going to draw this very quickly. So I'll try my best to make it look beautiful. Here we go. So if x approaches positive infinity, this is x approaching positive infinity, you see that the values of y are getting very close to y equals 0, so very close to the x-axis where the y values are 0, but there will always be above it, so that's 0 plus. And as x approaches negative infinity, this is where x approaches negative infinity, the y values will get very close to the x-axis. That's where the y values are 0, right? The graph will get very close to the x-axis, and the y values will get very close to 0. And it will be below the x-axis, which means the values of y will be less than 0, so 0 minus in the negatives. So now let's take a look at another rational function, still very simple because this time we have still a constant divided by a linear expression. So again, in the same way, we will substitute x by infinity, so negative 3 over infinity minus 2 will give negative 3 divided by positive infinity, and that would be 0 minus. So the next one, in a similar way, we'll have negative 3 over, this time, negative infinity minus 2. That's negative 3 over negative infinity, and that will give a positive 0. So a very small number, but because both these quantities are negative, they will give a positive here. If we were to graph this function, you can easily do this on Desmos, but if we were to graph this, then we will have the asymptotes at x equals 0 for the vertical, y equals 0 for the horizontal asymptote, and the graph of this function will appear in quadrants 2 and 4. And when x approaches positive infinity, you will see that the graph will approach the x-axis from below, and this is where the y values will be close to 0, and since we're below, 0 minus, so that makes sense. And similarly, when x approaches negative infinity, this is x approaching negative infinity, the graph is getting very close to the x-axis from above it, and on the x-axis we know the values of y are 0, and since it is above, is 0 plus. Now let's take a look at a real example. Well, the previous examples were real too. There is no doubt about that. So we're going to take a look at example 4. So we'll try direct substitution. And from the tone of my voice, you probably recognize that it may not work, but maybe, who knows? So I will substitute x by infinity, just like I did before. Let's see what happens. We should always have hope. Okay, so infinity plus 2 is infinity, infinity plus 5 infinity, and wait a second, we said this doesn't exist. We cannot divide two indefinite numbers. So we're going to say, well, what was the trouble here? The trouble here is that we ended up having infinity in both numerator and denominator, in both sides of the fraction. If we had a constant, it would have been fine, but we don't. So the trouble is having infinity in both numerator and denominator, but what brought infinity in the numerator? Well, the presence of x. And what brought infinity in the denominator? Also the presence of x, the presence of a variable. So that means that if we want to estimate this limit, then we need to remove the presence of x. in some ways. So the only way we know how to do this is by factoring out x from both numerator and denominator. And step number one in evaluating these type of limits would be by factoring out x of the highest power, and we have the power of 1 in both numerator and denominator. So we're taking x out, which means we have 1 plus 2 over x now here. And factor out x from denominator, 1 plus 5 over x. So now we have removed the problem we had. We had an issue with x, which brought infinity over infinity here. And now we simply have to estimate this limit. So x approaching infinity. And then we have 1 plus 2 over x, 1 plus 5 over x. Obviously, we can continue with, from here, we can continue with the substitution. But again, I like to show my steps when I explain the things. But we know what to do on an evaluation, what steps are necessary and what aren't, because we also need to save time, not only to show our thinking, but time management is important when we write tests and quizzes. So here we go. We substitute x by infinity, 1 plus 5 over infinity, and we know that we divide a constant by infinity, we get 0. So therefore, we're going to say that we're going to have 1 plus 0 over 1 plus 0 here, and that will give basically 1 over 1, so therefore the limit would be equal to 1. Now remember, this is an estimated value of the function as x approaches infinity. If we want to know exactly if it is more or less than 1, what you want to do is substitute infinity by a very, very large number, but make sure to use the same large number to both numerator and denominator. So 1, 2, 3, 4 zeros, and that could give you an idea whether this would be a 1 plus and a 1 or a 1 minus. So for now, we're going to be happy with just estimating the value of the limit, and we're going to say that is equal to 1. And once we're done, we are going to write the steps in here. So step number 1 is factor x of the highest power from both numerator and denominator. And we're going to see this in other examples, but when we say x of the highest power, sometimes we may not end up taking out the same power. So we may have a higher power in the numerator, higher in the denominator. You have to take out the highest power of the numerator, the highest power of the denominator. But we'll explain that in the coming examples. And then once we do that, we simplify the common factors. And lastly, we evaluate, or should we say estimate? Because it really is an estimation. And voila, we're done. We have another example here. You can try this on your own. And I will move on to example number 5. And obviously you have the solutions here posted online for our course. So it's easy for you to check your answers. And here we go. We're going to try another limit here. We have 2x to the 4 minus x squared plus 8x over negative 5x to the 4 plus 7. So if you substitute infinity here for x, then we get infinity minus infinity plus infinity. It will be a total mess of infinities here, which we cannot define. But it will be some infinity, I guess, and there will be infinity waiting in the denominator, so this is definitely undefined. So it's an indeterminate form limit. So I'm going to use the steps, or follow the steps that I wrote down in the previous examples. I'll factor out highest power of x from the numerator. So the highest power I see here is a power of 4. So that's the power that is coming out. And the rest of the expression now is 2 minus 1 over x squared. And notice how much more easily we can do this now, right? So factoring out such a great power. So in the denominator, we'll have x to the 4 coming out. That's the highest power we see in the denominator. And negative 5, and then plus 7 over x to the power 4. So we are going to take out this part that brought us the trouble of having too much infinity in both numerator and denominator, and let's see what happens. So I'm going to rewrite this step in here. And again, I keep repeating myself, but you can start substituting at this point. So the limit now is simplified to this. And now we're free to estimate it at negative infinity, a positive infinity, sorry. So here we have a big fraction. Write clearly. Write the big fraction line aligned with the equal sign. It is very important how we organize the work because sometimes we misread our own work. It has happened to all of us, just to make you feel better. And not only that, but it is the reality. All right, so here we go. 8 over infinity cubed, negative 5, plus 7 over infinity to the power 4. So we're simply estimating here, so we're not interested in the 0 minuses and 0 pluses, but we know this is a 0, this is a 0, and that's a 0 as well. So what that means is that we have 2 in the numerator, and we are adding and subtracting some zeros, so basically 2, around 2. And the denominator has negative 5 plus some zeros, so that's about negative 5. So 2 over negative 5, it's in the most simplified form, and that would be the value of the limit of this function at infinity. So 2 over negative 5. Now, in the next example, I suggest you try this on your own, but we did do this in class together. We are going to do this in class together to take it up. So this time we still have a rational expression, a rational function. We're finding the limit at infinity, but the new thing is that there is a square root involved in it. So we're going to follow the steps in the exact same way we wrote them down because they should work for any type of limit to infinity. So limit as x approaches infinity, fraction, okay? So if you look at the numerator, we have a square root, and whenever we see we deal with a multiple problem or multiple problems, so when we have different problems to solve in, say, in an expression, we tackle them one at a time. So I'm not going to worry about the square root. I'm just going to go for my first step in here. I'm going to take out the highest power of x, which in this case is x squared. So it will have to stay inside the bracket for brackets right now, inside the root. So we have 3 plus 6 over x squared. And then down in the denominator, we have the common factor, which is x. And then we have 5 over x, and then minus 2 here. Some people like to reorder the terms, so highest to lowest degree. Do that if that makes you happy. And it is important we're happy and feel confident about how we perform the solution, because more understanding means more accurate answers. And enjoying the work, why not? So notice here we have the product of two things, so x squared and this one here. So they're inside the root. And when that happens, we know that the square root of two things multiplied is the same thing as if multiplying each square root. So we'll do that. So we have the square root of x squared, the square root of 3 plus 6 over x squared. And that would be over x, 5 over x minus 2. As you can see, we're arriving to the end of our solution. Here we have the limit as x approaches infinity. Isn't this fun to write in every step? So remember that x is approaching infinity. Root of x squared will be just x. And then the square root of, 3 plus 6 over x squared. And then over x, now we can see them more easily, the common factors I mean, and then minus 2. And now we're going to kick them out of the expression because they brought enough trouble. And I will rewrite the limit one more time in the most simplified form. So we have the square root of 3 plus 6 over x squared over 5 over x minus 2. So it's time to celebrate evaluation of this limit now. And we have 3 plus 6 over infinity squared over 5 over infinity plus 2. So we know that dividing a number by infinity will give us 0. We're going to have 0 here, and that's a minus, obviously. And we're going to say that in this case, we end up with a 3 in the numerator, a negative 2 in the denominator, and 3 over negative 2 will be the value of the limit at x as x approaches negative infinity. Okay, so sorry, that's inside the square root. Very clever. So it's going to be square root of 3 minus 2. And here we go. That's the answer. I hope this made sense. It was a little bit of a long video, but remember that limits at infinity can be found in polynomial functions, right, by factoring out the highest power. And in rational functions, we take out the highest power from numerator and the denominator. And if we deal with rational functions that involve radicals, we follow the same process fearlessly. So do not worry about having a radical. Just factor out the highest power of the variable and then keep that inside the square root. And don't forget any square roots at the end. Thank you very much for learning with me, and I hope you found this useful. Bye for now.